Hey, hi folks. Chris McClure here. Welcome back after the Memorial Day holiday weekend. Now we're going to continue our discussion of review topics. Now we're going to refresh your memory about what polynomials are. Polynomial is nothing more than one or more terms of these things called monomials. Well, a monomial, of course, you know the prefix mono means one. And here exactly is the form of a monomial, where we have a variable, x in this case, but it could be t or y or z or any other variable, where you have a constant a times the variable x or whatever raised to some power k. And this power k, a number, has to be a positive or even zero, but cannot be a fraction. It has to be a whole number. So a is the constant, x is the variable, and k is the power. It's an integer, a non-negative integer. Now the variable a here, the constant a here is called the coefficient, and k is the degree of the monomial. So the power is the degree of the monomial. So for example, if you have the monomial 6x squared, then 6 is the coefficient, and the power 2 is the degree of the polynomial, or of the monomial. And negative square root of 2 times x cubed, well, negative square root of 2 is the coefficient, 3 is the degree. Now, any integer, any real number itself could be a monomial. Think about this as 3 times x raised to the 0 power, where 3 is the coefficient and the power is 0, so 0 is the degree of this polynomial. So a real number by itself is a monomial of degree 0. Okay, negative 5 times x, it has a coefficient of negative 5 and a degree of 1, because you could write x as x raised to the 1 power. X to the 4th power is a monomial with coefficient of 1 and degree of 4. You know that the coefficient is 1 because when you don't see a number in front of x, well, by default that number is 1. It's like a ghost. It's there, but you don't see it, but you could pull it out at any time. And now notice that 3 times x to the 1/2 power is an example of a term that is not a monomial, because this exponent is not an integer. It's a fraction. Likewise, 4 times x to the negative 3 power is not a monomial, because this exponent is not a non-negative number. All right, when you have a negative integer, a negative exponent, then we do not have a monomial. Now, a polynomial is going to be one or more monomials. So here we've got a monomial and another monomial and so forth. So you got the sum of several monomials. In fact, a polynomial is one where you have one or more monomials. So a monomial by itself is a special version of a polynomial, and so forth. So what we typically do with the polynomials, we arrange it with the terms going in decreasing power. And so n would be the highest power. The coefficient for this highest degree term is called the leading coefficient. Okay, and this term right here with the highest degree is called the leading term, with n being the degree of the polynomial. So negative 8x cubed plus 4x squared minus 6x plus 2 would be a third degree polynomial with a leading coefficient of negative 8. And you'd have coefficients of negative 8, 4, negative 6, and 2. Now, when you have missing terms, you can still talk about what the coefficients are. For example, 3x squared minus 5 is a second degree polynomial. Notice that there's no x term, but you could fill in the x term by writing 0x. So you have coefficients of 3 and 0 and negative 5. It would be incorrect for you to not list 0 as a coefficient. If you have to correctly list all the coefficients, the 0 for the x term would be included in that list of coefficients. 8 minus 2x plus x squared, just rewrite that in a descending form, and that x squared could be thought of as 1 times x squared plus negative 2x plus 8. So this is in descending form, where the powers are descending as you go from left to right. And you have coefficients of 1, negative 2, and 8. Second degree polynomial. Over here, we've got 5x plus square root of 2. This is a first degree polynomial with coefficients of 5, square root of 2. Here we've got the polynomial of 3. It's a perfectly good polynomial. It's a 0 degree polynomial, because you could write it as 3 times x to the 0 power with a coefficient of 3. And 0 itself is a polynomial. It has a 0 as a coefficient. And by default, we considered a no degree, not 0 degree, but a no degree polynomial. Now we're going to talk about treating polynomials as numbers where we can add and subtract them. So for example, if you have this polynomial and this polynomial, we can simply add them by adding the like terms. So the x cubed terms will add together, the x squared terms will add together, and so forth. And you add those like terms together by adding the coefficients together. So you just group the like terms together. So this 8x cubed plus the negative 2x cubed, they can be grouped together, and so forth for those other like terms. And go ahead and add those coefficients, and there you go. And that's all there is to adding polynomials. You could also add polynomials the vertical method by, stacking the polynomials on top of each other, lining up the like terms, and just adding the coefficients. Moving along here. Subtracting polynomials, same concept here. Make sure that you correctly observe the order of subtraction and that you perform subtraction between like terms, like you see here. By the way, one common mistake here is failing to carry the subtraction through to all the terms in the second polynomial. So a common word of advice is to just simply switch the signs in the second polynomial and then add. Okay? Because after all, subtraction is the same thing as adding the negative of something. So if you just take the sum of the negative of the second polynomial, then that's the same thing as subtraction. And there's the difference. And of course, the same discussion regarding vertical stacking of the polynomials, where you stack one polynomial, the first polynomial, on top of the second polynomial to be subtracted. And you are going to just either subtract the coefficients, or you can add the negative of the coefficients. Take the first coefficient plus the negative of the second coefficient on a term-by-term basis. get the same thing. Moving along here, multiplying polynomials, just like you can multiply any two numbers. Then you are basically going to do repeated applications of the distributive property. Now you could either take 2x plus 5 times x squared times negative x and times 2, and then distribute each of those x squared, negative x, and 2 across the 2x plus 5, or vice versa. You could take, the x squared minus x plus 2 and distribute that across the 2x plus 5, like we see here, and then distribute the 2x across the x squared minus x plus 2, and also distribute the 5 across the x squared minus x plus 2, and then add like terms and simplify. Okay? Another way that you could do multiplication for polynomials is to stack the larger polynomial on top of the smaller polynomial and just multiply out like you would with multi-digit numbers. Okay, I'll let you look at that, see if you have any questions. There are some special products that you will want to remember the formulas for. So for example, if you have one binomial times another binomial, then you can remember the FOIL, F-O-I-L, is an acronym that tells you how to do the product of two binomials, where you take the first terms multiplied together, which is the ACX squared that you see here. And then you have the outer, which basically means the first term of the first binomial times the last term of the last binomial. That's the so-called outer. The inner is the last term of the first polynomial of the first binomial times the first term of the second binomial. And you are taking the outer plus the inner, because they both have the x as the variable. And then finally the last terms of each of the binomials multiplied together. So you got your first, outer, inner, and last, FOIL. So we use FOIL as a generic term to talk about multiplying polynomials together by doing repeated applications of the distributive property. So there we FOILed x minus 3 times x plus 3. By the way, when you see a binomial times its conjugate, you're always going to have this difference of squares sort of thing, because the outer and the inner terms will cancel each other out. For part B, we actually are doing the square of a binomial, x plus 2 in this case. And notice that the outer and the inner products are the same. So you'll just basically have 2 times the first times the last. So 2 times 2x. That'll be the middle term of the product. And same thing for x minus 3 squared. Notice that 2 times negative 3 times x, which is negative 6x, that's the middle term of the product. Here we got x plus 3 times x plus 1. We'll just FOIL it out. Notice that this 4x right here is the result of taking the outer plus the inner. In other words, if you take this 3 plus this 1, you add up those last terms, that's where this 4 comes from. And here for part E, 2x plus 1 times 3x plus 4, go ahead and FOIL that out. 2x times 3x is 6x squared. 2x times 4 is 8x. 1 times 3x is 3x. And 1 times 4 is 4. and then add 8x plus 3x, and you get 11x. So where did this 11 come from? Well, you'd have 2 times 4 plus 1 times 3. So 8 plus 3 is 11. There you go. And this 4 right here is the result of taking this 1 times this 4. Okay. Now, we're going to later on be talking about factoring. So after you get the hang of multiplying, we're going to be doing the result, or the opposite of this result. We're going to be taking the second degree polynomial and decomposing it as the product of two binomials. So take a good hard look of how this went. See this 11x? Imagine working backwards and saying 11x is the same thing as 8x plus 3x. Okay? I'll let you look at that for another couple seconds. All right. Now, as I mentioned before, when you have difference of squares, that's going to be the result of taking a binomial times its conjugate. And conjugate for a binomial is, if you have subtraction in the one, then you have addition in the other, or vice versa. So you got a binomial times its conjugate. So you'll always have this difference of squares. If you have a binomial squared, then you're going to always have this form here or here, depending on if this is a plus or a minus. Then this will be a plus or a minus there. But this second sign will always be plus. All right, let's look at some more practice here. X minus 5 times x plus 5. Again, these are conjugates of each other. So all you have to do is simply write x squared and then a minus 5 squared. So in other words, x squared minus 25. A difference of squares. X plus 7 squared. And so you know that automatically you're going to have an x squared and a 7 squared, and also a 2 times 7 times x as the middle term. And 2 times 7 times x is 14x. So there's that special form of a perfect square, where you have x squared here and a 7 squared there, and you should have a 2 times 7 times x here in the middle, in order for this to be the square of a binomial. Kind of the same thing for the 2x plus 1 squared. So you know that 2x squared is 4x squared, and 1 squared is 1, and 2 times 1 times 2x is 4x as your middle term. 3x minus 4 squared. Again, 3x squared is 9x squared. And negative 4 squared is 16. And then for the middle term, you should have negative 2 times 3x times negative 4, which is negative 24x for your middle term. Now let's do some cubing here. X plus 2 cubed. Well, you could think about x plus 2 cubed as x plus 2 times x plus 2 squared. But x plus 2 squared is x squared plus 4x plus 4. But then you can go ahead and multiply the x plus 2 times its square. And if you look at this result, you might discern a certain pattern. We'll explore this pattern here soon. Here's x minus 1 cubed. So again, we'll do the same strategy here. X minus 1 times x minus 1 squared. But x minus 1 squared is x squared minus 2x plus 1. And then multiply it out. Now, do you recognize this pattern here? The x cubed minus 3x squared plus 3x minus 1. Notice the alternating signs here. That's an important clue. And also this 3 and this 3, that comes from somewhere. Now here is the pattern here for cubes. If you have x plus a cubed, then x cubed plus 3ax squared plus 3a squared x plus a cubed, then is going to be the result. And likewise for the x minus a cubed, but you'll have alternating signs. So let's take a look at this one right here. X minus 1 times x squared plus x plus 1. What's going on with that? Well, let's go ahead and multiply this out and see what you get. And it turns out that's x cubed minus 1. So there's the factorization of x cubed minus 1. So you pull out an x minus 1, this is what you get left over. Okay, so that is something worthy of remembering. All right, here's another one, but this time you have a sum of 2 cubed. Now let's multiply the x plus 2 times x squared minus 2x plus 4. And that works out to be x cubed plus 8, as in x cubed plus 2 cubed. So you can factor x cubed plus 2 cubed as x plus 2 times x squared minus 2x plus 4. So you got difference of cubes and sum of cubes. Ways of factoring them. All right, now let's talk about division. Now, if you remember how to do long division with multi-digit numbers, then you'll see that this is very similar. All right, now just to refresh our memory, let's see how we did long division 842 divided by 15. This is how we wrote it. Take a look at 15 and how that relates to 84. How many times does 15 go into 84? And the answer is 5. 5 times 15 is 75. Subtract, you get 9. Bring down the 2. How many times does 15 go into 92? The answer is 6. Multiply. 6 times 15 is 90. Subtract, and you get 2 as the remainder. So you could write 842 divided by 15 as 56 remainder 2. As in 56 and 2/15. Okay? That sound familiar? Well, we could also write our number like this, where you have your dividend, which was 842 in this case, as your quotient times the divisor plus the remainder. This will be something important for you to remember later on. But if you're not sure, we'll just take a look at this equation right up here and multiply through by 15. And when you do that, you'll have 842 is equal to 56 times 15 plus 2. Now let's take a look at how this goes for polynomials. Let's take a look at 3 times x cubed plus 4x squared plus x plus 7 divided by x squared plus 1. We can go ahead and put the quotient of 3x cubed plus 4x squared plus x plus 7 under the division symbol and with an x squared plus 1 out front. And then we can compare leading terms, x squared versus 3x cubed. And if you were to just mentally do a little division, 3x cubed divided by x squared, you get 3x. So that goes up there. And then multiply 3x times x squared plus 1. And this is what you get, 3x cubed plus 3x. Make sure that you line up the like terms. Subtract. And when you subtract, this is what you get, 4x squared minus 2x plus 7. X squared goes into 4x squared how many times? The answer is 4. And then multiply 4 times x squared plus 1 is 4x squared plus 4. subtract, and notice that the negative 2x plus 3 is smaller degree compared to x squared plus 1. That means that you're done dividing, and 3x plus 4 is your quotient, and negative 2x plus 3 is your remainder. So you could write the quotient 3x cubed plus 4x squared plus x plus 7 divided by x squared plus 1. You could write that division as 3x plus 4 plus negative 2x plus 3 over x squared plus 1. All right, and then I'm going to quickly go through this next one. X to the fourth minus 3x cubed plus 2x minus 5 divided by x squared minus x plus 1. Again, you see the setup there. Look at leading terms. X squared goes into x to the fourth. X squared times, multiply, here you go, subtract. And then again, how many times does x squared go into negative 2x cubed? The answer is negative 2x. Multiply, subtract, and so forth. Point here is that you just keep on plugging along until you get this resulting polynomial down here that's a smaller degree compared to the divisor. So you have the quotient of x squared minus 2x minus 3 with a remainder of x minus 2. Take a look at this theorem. So suppose that we've got a polynomial, call it q, of a positive degree, so not a 0 degree, but a positive degree, 1 or greater, and let capital P be a polynomial whose degree is greater than or equal to the degree of q. So P is the bigger polynomial, Q is the smaller polynomial. The remainder after dividing P by Q is either the 0 polynomial or a polynomial whose degree is less than the degree of the divisor Q. Should make sense. As a matter of fact, the degree of the quotient plus the degree of Q should be equal to the degree of P. All right, we have a lot more to talk about regarding factoring polynomials. So now let's talk about polynomials when you have more than one variable. So for example, if you have x and y, here's one possibility of having a 2-degree polynomial. By the way, this is a 4th-degree polynomial if you were to add the degrees of the polynomial, of the variables. So 3 plus 1. This is a 2nd-degree term, a 4th-degree term, and a 0-degree term here. Here you got a 3rd-degree term and a 2nd-degree term. So this is a 3rd-degree polynomial versus a 4th-degree polynomial for the first one. Over here on the right, all of these terms are 4th-degree terms. Because if you were to add up the exponents, even though you don't see the one there or the one there, add up the exponents for each term, you get 4. So this is a 4th-degree polynomial. Let's take a look. 2x minus y squared. FOIL that out. This is actually a square of a binomial. And this is your result here. Notice that the first term of this product polynomial is the square of 2x, right? 4x squared. And of course, negative y squared is y squared, right? And then 2 times negative y times 2x is negative 4xy. So we have a 2-variable polynomial, 2nd degree in this case. So you'll get the chance to do some playing around with single variable polynomials, multivariable polynomials, adding, subtracting, multiplying, dividing. Okay, so we'll leave it there for now, and we will move on to section R5 tomorrow. Have a good day, and I'll see you next time.